Okay, here's the theorem. It says continuity implies integrability. That's the name of the theorem. And you know what the theorem says? It says continuity implies integrability. So there you go. The theorem is named after what the theorem says. All continuous functions are integral. That is, if a function is continuous on the closed interval, it's integrable on the closed interval from a to b. Now, what does integrable mean? We've seen that word already. It just means that you're able to find an area under the curve. Okay, that's what it means. You're able to find an area or a net accumulation. So if you use it using letters here, you got C implies I. That's what we read. That's the statement. And of course, these symbols in front mean not. And this would be true also. If it's not integrable, then it is not continuous. And that would be the what of the statement, just to review. Contrabassoon, contrapositive, yeah. Contrapositive, good. So remember, for any statement, the contrapositive is true. So differentiability, of course, implies continuity, and the contrapositive was useful because if it wasn't continuous, it wasn't differentiable. So now here, differentiability really also now implies what? Integrability by the transitive property, so we call it. D implies C and C implies I, so D implies I. So therefore, if it's not integrable, it's also not differentiable. Now notice what the theorem does not say. It doesn't say if it's not continuous, it's not integrable. It doesn't say that. There are some times where we can have like a function that's not continuous. For instance, if I have a graph like this, and there's a hole right there, and I want to integrate from A to B, that would end up being the area of the region, right? This function is not continuous. Does that mean it's not integrable? No. As it turns out, it is integrable still. The hole is not going to really be a problem in terms of finding the area of the region because we can infer what is there. So holes aren't going to necessarily keep something from being integrable. You'll see later when we study indefinite integrals, we can even sometimes, but not always, integrate through a vertical asymptote. And that's kind of weird too because a vertical asymptote is unbounded, so we'll be finding finite areas of infinitely large regions, or I should say unbounded regions, and that's kind of weird too. But here's what we know. We know that if it's not integrable, then it's not going to be continuous. And if it is continuous for sure, if that hole wasn't there, then there's really no problem at all in finding the integral. Okay, so that's what that means. All right, so let's kind of shift gears here a little bit. We started off by looking at some tedious methods for approximating area. We had a function, we had to identify the region, we had to partition it ourselves, we had to find our own x values, and we had to find our own y values. That's still all good, but there's quicker ways to kind of answer those types of questions, and they typically show up quite a bit on tests. Example 8 is one such case. It says, if f of x is a continuous function. Oh, now that we know it's continuous, we know it's also what? Integrable. Very good. Such that f of x is greater than or equal to 0. That means that the entire function is non-negative, okay, for all x in the whole wide world, given selected values of f below. Approximate. There's your squiggle alert, right? Squiggle alert. Approximate the integral from 0 to 3 using numeric methods. Okay, so this is not going to be the vague instructions I give you on an exam or anything. I knew that I was going to walk you through this. We're going to practice all of our methods. That's why I did that. Normally, you're going to be given the method to use, either the midpoint, the left endpoint, right endpoint, or the, what's the other one? Trapezoidal. Yeah, we're going to do all of them. Okay, so we have f of x here, and notice the y values are 2, 4, 6, 7, 4, 1, 5. We don't have the values in between 0 and a half and 1, but we do know that the function values that are not listed, we know that they're not negative. That's kind of important. The first thing you want to do is, I guess, look at what the question is asking. We're trying to approximate the integral from 0 to 3. You might be given more values than you need. Well, notice the chart does span from x equals 0 to x equals 3. The chart does span from 0 to 3. If the chart spanned from 0 to 4, you wouldn't be using all of the information in the chart. So that's been kind of a late trend to give you more information than you need, okay? The next thing you want to do is see what delta x is. Because when you're given an equation, you're allowed to find your own delta x, and it can be uniform. But when you're given a table of values, you're at the mercy of the table, right? So let's go ahead and see. From 0 to 0.5, that's a half unit. From 0.5 to 1, that's a half. That's good. From 1 to 1.5, that's a half. From 1.5 to 2, that's another half. I guess it's in a half so far, so it must be half all the way through, huh? Don't assume that. No, don't assume that. Because they would be just like me to change it on the very last one. Well, it does turn out that the x's are changing by equal increments of 1/2. Okay? So that's your delta x. Now, to be as accurate as possible, it usually says use as many subintervals as indicated by the data. How many subintervals can I use then? Well, yeah, just count how many 1/2s you have. 1, 2, 3, 4, 5, 6, right? We have 7 values defining 6 intervals. So that's another reason maybe you calculate your subintervals, because that's going to be how many rectangles you have. You're going to have 6, all right? So let's go ahead and do the left endpoint first. So we're going to say that is going to be approximated by L sub 6, which equals. Now we can go straight to the expedited part because delta x is uniform. And remember, width times height plus width times height, we can factor out the delta x, which is 1/2. Now for a table of values, if you were to do it, remember the left endpoint says on your first interval from 0 to 0.5, you're going to define the height of the rectangle by using the left endpoint, which is x equals 0. So what is f of 0? It's 2. So you would have as your first area 1/2 times 2. The next interval from 0.5 to 1, you would use its left endpoint, so it would be 1/2 times 4. So notice if you're factoring the 1/2 out, it's super easy. All you have to do for the left endpoint method is add up the first 6 y values. So you got 2 plus 4 plus 6 plus 7 plus 4 plus 1. Do you add the plus 5 at the very end? No. It's left justified. With 6 subintervals for any Riemann sum or any rectangular method, you're going to have as many terms as you do partitions. 6 partitions, 6 rectangles, 6 y values, okay? It's the trapezoid that it uses all and has 1 extra. Now, if you want to figure that out, go for it. I don't. Yeah, let's see who can get it. Can I get it? 10, 20, 12? 12? Okay, good. All right, so the next one. The integral from 0 to 3, we're going to say squiggles. Let's do r of 6. R of 6. Well, can we still factor the 1/2 out? Indeed, yes. Now, if we were going to do this, which would be the first y value we'd start with? We would right justify the first interval. If you want to keep starting on the left, the first interval from 0 to 0.5, it would use the y value now at 0.5, which is 4. So you're skipping the first one and starting with 4. So 4 plus 6 plus 7 plus 4 plus 1. And now you're using the last one plus 5. So it's right justified. If your delta x is uniform, some people prefer just to start at the right and add up the first 6, which still makes you skip the second one, or the first one, which is number 2. But if your delta x is not uniform, as you'll see here shortly, you can't do that. So I wouldn't recommend that as just a general method. So left justify the first 6 for the left endpoint, skip the first one, and right justify for the right endpoint. And does that come out to be anything nice? 27 halves? Okay. Is that 12-ish? Yeah. Some of these may or may not even be really close to each other. Now the midpoint. Can I use the midpoint with 6 subintervals? Well, let's see. If I was going to use 6 subintervals, I would need to know the y value halfway between 0 and 1/2, which would be a 4th. Do I have that value? I don't. Okay? So I can't use 6 subintervals. But maybe I can use 3 subintervals. Maybe. If I use 3 subintervals for the midpoint, My delta x from 0 to 3, that'd be 3 minus 0 divided by 3 would be 1. I'd have to count by ones, right? I'd go from 0 to 1. I'd go from 1 to 2. I'd go from 2 to 3. And I might be able to pull that off because halfway between 0 and 1 is a half, and I know its y value. And halfway between 1 and 2 is 1.5, and I know its y value. And halfway between 2 and 3 is 2.5, and I know its y value. So, again, if you have a uniform delta x, or if every, or at least if you have even partitions twice in a row, they could change, but they have to be consecutive twice in a row. You could still do a midpoint approximation, but you're going to have to use fewer subintervals. And so, I don't know, does that decrease the accuracy in general? Maybe. All right, if we're choosing our own values, of course, we find new x values and we can generate it. What's our new delta x if I'm using 3 subintervals? It's 1, right? Times, and then the y value at the midpoint would be 4, and then 7 and 1. So 4 plus 7 plus 1. And that comes out to be 12. Happens to be the same as the left endpoint. Now, the trapezoidal. T sub, can we go back to 6 with the trapezoid? Yes, we can. Now, the trapezoidal one is the one we just learned yesterday. What always goes out front for the trapezoid? 1/2, always. And because it's a uniform delta x, we can also pull delta x out. Delta x, then if we go back to 6 subintervals, is again 1/2. So 1/2 delta x. And remember, for the trapezoid, with 6 partitions, we're going to have 7 terms because we're going to use all of them. But we do what on the ones on the interior? We double them, okay? So here we go. If you're doing this on a free response, be careful not to double the values in your head, because then you're not going to be numerically indicating your method. If you show the table values in your calculations, then it's indicating your method. So here we go. It's 2 plus, and now twice 4, plus twice 6, plus twice 7, plus twice 4, plus twice 1, and then the last one is plus 5. So speaking of a free response, that right there would get 2 checks. It's a 2-for-1 deal because, number one, it indicates your method. I can see the 1/2, I can see your delta x, and I can see every number from the table in your calculations. But it's also a numeric answer, and so you can walk away and you're going to get credit for the right answer. So that's another thing that we want to be thinking about as we move forward. Don't try and do too many things in your head. It's tempting to call that like 8 and 12 and 14. But if you do that on a free response, you're not going to get full credit unless you write like, you know, f of 0 plus twice f of 1/2 plus twice f of 1, and then you can do anything after that. You can add it all up in your head if you want. So it's all about indicating your method, showing your process, and then getting a numeric answer, and that's a 2-for-1 deal. Now that right there should be equal to, let's see, 51/4, I believe. Is that right? Yeah. And I didn't get that by evaluating that. How did I get that? Yeah. Remember, that's true. The trapezoidal approximation is always going to be the average of your left and right endpoint. So if you average 12 and 27 halves, you get 51/4, and I'll leave it to you to verify that that's what that's equal to. So if you're ever asked to find in sequence the left endpoint, the right endpoint, and then they ask you for the trapezoidal, you're welcome to say T of 6 equals, I would go ahead and use the number you have here, 12 plus 27 halves all over 2, so that you're, again, indicating your method with something that you previously had. But very seldom do we do that. It's usually like, here's one method, go with it. And so I don't think it would be the best way to get the trapezoidal by first doing left and right and then averaging them. You just go straight to this pattern. But it's up to you. Is there a way to tell which of those is more accurate? No. All things being equal with the same number of subintervals, remember the midpoint and the trapezoidal in general are the more accurate. But in this case, because we had to compromise our subintervals for the midpoint, It have fewer subintervals. I don't think we can throw it in there as being the most accurate. So maybe the trapezoidal, maybe it's the one that's closest to the actual. But we don't know because we don't know the actual. Now here's just a question based on what we're doing today. Could any of those represent, I wouldn't want to say the area, but the approximate area? That's a better word to throw in there. Could any of those represent the approximate area of the region bounded by the curve from 0 to 3? Well, maybe, right? The only time a definite integral is going to represent the area or an approximation of the area is if the function itself is what on the entire interval? Positive or non-negative. Is our thing non-negative? Yes. Now, it's only because it said that up here in the instructions. If they didn't say that, could you just look at the y values that you're given and say, oh, all the y values are positive? Would that work? No, because without saying that they're positive everywhere, it might go as it goes from 0 to 0.5 and from y equals 2 to 4, it might go from 2 down to like negative 5 million and then back up to 4. Ooh, that's way down there, right? You don't know. You have no idea what's happening in between the values are given. So don't assume that. But because it said that, now we can say, yeah, all of them actually now do represent approximations of the area. Are you catching a fly? No, a mosquito. Hey, look, a little bonus review question. Also, approximate f prime of 1. Good old review. F prime of 1. That's the slope of the tangent line at 1. We can't actually find it because we don't have the equation. So to approximate a tangent line, we have to use a secant line. So here we go. F prime of 1, squiggles. And remember, there were some criteria on what to do. Notice that 1 is in the chart. The value to the left and the value to the right, the x values, they're equidistant from 1. So this is the one where you actually have 3 options to compute it. You can use the point you want and the one to the left, the point you want and one to the right, or you can use the 2 on either side. So you could say it's, now I'm not going to use f of 1. I'm going to go straight to the y values. It's going to be either 6 minus 4 over 1 minus 0.5, or it's going to be 7 minus 6 over 1.5 minus 1. Or you could use the 2 on either side. You could say 7 minus 4 over 1.5 minus 0.5. And speaking of 2 for 1, here's another 2 for 1. Difference quotient is shown in all of those 3. So that's indicating the method. And they're also numeric answers, since I didn't say f of. I actually used the numbers from the chart. Now, guess what the most common mistake is? I think I mentioned this when we went over this the first time. Remember, your table of values has the x values on the top and the y values on the bottom. It's a very easy thing to say 1.5 minus 1 over 7 minus 6, right? Because that's how they're situated. If you did that and this were worth 2 checks, would you get any checks for that? If you wrote down 1.5 minus 1 over 7 minus 6? You definitely wouldn't get the right answer check, but you would, believe it or not, get a check for having the difference quotient. Yeah, so we're after both checks, though, right? So just be very mindful, be very aware of that. Okay, that's pretty quick and easy. When you don't have to generate your own values, they're given to you in a table of values. Very quick, very easy. Any questions on that? Are the subintervals always going to be equidistant? Are they always going to be equally spaced? I don't think so. I hope not. That would be boring. Okay. Example 9. F is continuous. That means it's integrable for all x. Given selected values, approximate the integral from 1 to 8 using numeric methods. Reread the definite integral. Okay. The integral from 1 to 8. Okay. The data spans from what? 0 to 10. Ooh, okay. We're not going to be using this guy here. Would the AP exam write something like that? Reread the definite integral? No. Okay. Also approximate f prime of 7. Okay, whoa, first things first. Ah, we can get rid of 0 too. Good eye, good eye. I was about to calculate the width so I can get rid of 0. Dang, I tricked myself on that one. All right, so now we're there you go. We'll go like that. We're focused on 1 to 8. Let's calculate the subinterval widths. 1 to 3, that's 2. I guess it's 2 all the way through, right? Delta x is 2. It's 3 there. Okay, so now delta x is the average of those, right? 2.5? No. It's 0.6 here, and it's 1.4 there. Okay, do we have a uniform delta x? No. So we're not going to be able to factor it out. It's not going to be there in each term. So we're not going to be able to expedite the process, but it's still not going to be that difficult. Here we go. The integral from 1 to 8 with respect to x, dx, squiggles, L of. Well, let's see, how many subintervals is that going to allow us? How many delta x's did I compute? 4. Okay? So we're not using all the data, but we got 4 subintervals. So L sub 4 equals, and here we go. The first width is 2. Now using the left endpoint, which y value do we use? The one at 1 or the one at 3? 1. The y value at 1, which is 3, not 3. Okay, we're using this 3. 2 times 3. You want to just call that 6 and save time? No, because then you're not indicating your method. Plus, the next width is 3 times the y value, which is 3. Plus, the next width is 0.6 times the y value to its left, which is 1. Plus, the next width is 1.4 times the y value to its left, which is 5. So notice we're still using just 4 y values, and they are left justified. We're not using the last, but they're each associated with their own unique width, right? Now, I'm not going to compute that because it's almost trivial at this point. That would be a 2 for 1, by the way, on a free response. R sub 4. Well, if you want to go through and write your widths out, it's 2 times something, plus 3 times something, plus 0.6 times something, plus 1.4 times something. And now all you're doing is, instead of starting with the first 3, you're starting with the second one, which happens to also be 3. And you got a 3, 1, 5, and then 8. So here's where you can't just start with the 8 and drop them in there from left to right, because they're associated with different widths. And that's another 2 for 1. Now, could you still do it like this if it were a uniform delta x? Sure, yeah, you can still do it like that. But it's required if delta x is not uniform. It's not that much more difficult. All right, can we do the midpoint here? Let's talk about that. Can we do the midpoint? Can we do the midpoint? Well, let's see. If I skip an interval from 1 to 6, what would be the midpoint between 1 and 6? The midpoint of two numbers is the average. So the average of 6 plus 1 is the average of 7, which is 3.5. Do I have the y value at 3.5? No. So I can't do a true midpoint. I could do some kind of like intermediate calculation, but it's not going to be a true midpoint. So I can't do that here. So we're not going to do the midpoint. But I will try a trapezoidal approximation. What can always come out front for the trapezoidal approximation? Always. 1/2. But now, since I can't factor out the delta x, it's just going to be the width, 2 times the sum of the two values. Okay, remember it uses the one on the left and right. 3 plus 3, is that 6? It is 6. Do I want to call it 6? No. I want to indicate my method. Good. Plus, the next width is 3 times the sum of those two y values, which is 3 plus 1. Plus the next width, 0.6, times the sum of the two y values on either side, 1 plus 5. And then plus, finally, the width of 1.4 times the sum of the two y values on either side, 5 plus 8. So it's nice to write the widths up there like I've been doing, straddling the gap in between there. It tells you how many subintervals you're going to have, and it's real easy then to like just go down to the left for your left endpoints. It's easy to go diagonally to the right for your right endpoints, and you can kind of see that it's including both left and right when you do the trapezoidal. There you go. Not that difficult, right? All right, so the last part here, or the two last parts, do any of these represent, again, I should say, an approximation of the area? Can we say definitively that any of them represent approximations of the area of the region from 1 to 8 on f of x? No. All the y values we used were positive, but as I mentioned before, some of the ones that we don't see could have been negative, and it did not say explicitly in the problem that it was greater than or equal to 0 for all values. So we can't assume it. All right, so the last thing is to review what f prime of 7 is. It's making my throat sore for some weird reason. I don't know. My throat is getting sore listening to that. I guess so. All right, f prime of 7. Is 7 in our chart here? 7's not in the chart. So, where would it live in the chart? It would live between 6.6 and 8. And so, in this case, you're going to have to use the 2 that are on either side of where 7 would live. So here we go. F prime of 7, squiggles, 8 minus 6.6 over 8 minus 5? No. 8 minus 5 over 8 minus 6.6. Yeah. Change in y, which is the second row, over change in x, which is the first row. And if there were any units, like sometimes there's units here, like feet, or sorry, let's do it this way. Let's do seconds and feet. Sometimes they do that. You'll see that when we get to chapter 6. If there are units, then you just put feet per second. But in this case, there's not. And that would be a 2 for 1. Okay, I think I'm going to stop there and try to recover. And we'll finish this section pretty easily, I think, on Tuesday. The integral of the unit of the integral would be feet. Yes. Yeah, very good. Okay, so we'll finish on Tuesday. School is optional on Monday. And we'll test next Friday. If you want to write that down on your calendar, we'll test next Friday.